In this class, we will discuss how a beam column structure can be analyzed. So this is an analysis type of problem wherein they will give the values of axial load as well as the moments acting at the ends of the beam column, something like this. So this you can take it as M1, M2, something like this, and this is your P value. So when this beam column is subjected to axial load as well as moments, then suppose if a section is provided for that, how to check the adequacy of that particular section? So usually ISHP sections are used because Indian standard heavy beam sections are used for columns. So some ISHP section is given or provided for this beam column of some length L. So we have to check whether the applied axial load or the moments at the ends, that means the section whether it can withstand those things. That is the problem of an analysis type of problem. In design problem, normally they will give the loads and the moments, and you will be asked to select a suitable section and check that section for the beam column. Whereas in the analysis type, already the section is provided and they will give the axial load as well as the end moments. You have to check whether that particular section provided over for that particular length it can withstand the given axial load and the moment. So of course we are using these three pages 70, 71, 72 of IS 800 for both analysis and design of beam columns. So the design analysis procedure is like this. They will give the length of the beam column, end conditions. So depending on the end condition, you can have the effective length. Then they will give the axial compressive load factored maybe. If they don't give the factored value, then you have to multiply it by 1.5 to get the factored value, and the end moments also will be given. So we have to check whether the section provided, ISHP section provided, is sufficient or can it withstand or is it adequate to take care of both the values of P, M1 and M2. The steps run like this. You have to mainly check for 4 different criteria. So that I am going to explain in this video. So all these equations, whatever are written, so they are all available in those pages 70, 71, 72, and also some other tables which I am going to tell you. So first what you have to do is, you have to note down the properties of the given ISHP section from the steel tables. Maybe ISHP 250 or ISHP 300 may be given. You note down the properties. So properties means all the values. So it will be like this. So you have to note down the width of flange, thickness of flange, thickness of web, overall depth, and depth of web you have to compute. Then IZZ as well as IYY. Then you may have to get the values of ZPZ, plastic section modulus about Z axis, and elastic section modulus about Z axis, ZEZ. So all those things are readily available from these field tables. So you have to note down for that particular section. Then you note down the values of Fy, gamma, M1, and alpha NT. So this alpha NT value is taken as 0.21 for road sections. This I have explained in the case of beams also for road sections. And gamma M of course is 1.1, and Fy depends on the grade of steel. For Fe 410 steel, Fy value you can take 250 MPa. So here, since the beam column is subjected to both axial load and bending, so we have to do the check for both combined effect of axial load as well as bending. That means we are using the concept of analysis of columns as well as analysis of beams. So both we are going to use now. Now the third step is you have to classify the section. Whatever section he has given, ISHP section, we have to classify that section, whether it is plastic section or compact section or semi-compact section. So depending on the values of that B by TF and of course B by TW, which I have explained in the design of beams, using this table 2, page 18 of the code. So you have to judge whether that section is compact or plastic or semi-compact. Then of course the loads will be given. If they give the service loads, you have to get the factored loads by multiplying by design load by multiplying by 1.5. So n value I am going to take as factored axial load, and factored bending moment I am going to take as mz. So next afterwards we have to compute the design compressive strength due to yielding. So this step starts now. ND value. So ND value, design compressive strength. So please note down the notations. So N is this value. Applied load is ND, factored applied load, and strength value is ND, which is given by the criteria due to yielding. Yielding criteria is used here. Yielding means that entire cross section of the beam column is considered. So ND is given by AG into Fi by gamma MO, where AG is the gross cross-sectional area of that ISHB section provided, which you can get from in millimeter square from the steel tables. Fy is of course 250 MPa and gamma MO is 1.1. So this is one value you are going to get. Of course this can be in newtons or kilonewtons. Then another design bending strength you have to calculate is the design compressive strength. Since the beam column is subjected to both bending as well as compression, you have to calculate the strength in both using for both the criteria. Of course, I am calculating along z-axis. That is denoted by mdz. Mdz is given by beta b into zpz into Fy by gamma MO, which we have used in the design of beams also. Same formula we are going to use. Where beta b is taken as 1 if the plastic is compact and plastic section, which we get from this step, and beta b is taken as zdz by zpz, the ratio if it is a semi-compact section, wherein this value is slightly less than 1, beta b will be less than 1 because zdz is less than zpz. Now after calculating this nd value, mdz value, we have to take two ratios. One ratio is this n, factored axial load, given axial load, divided by design compressive strength n by nd, plus mz is this given factored bending moment, divided by whatever we have calculated strength, the bending strength. So that sum of these two ratios should be less than or equal to 1. That is the first check. That check is called as local capacity, check for local capacity of the section. So this should be satisfied. This is the first check we have to do in beam analyzing beam column, or after designing also we have to check this. Now the second check is check for member buckling resistance in compression. Whether that member can resist the buckling. So for that, what we have to do, the steps are like this. We have to find the ratio h by bf. H is the overall depth. So that you know, overall depth of the section, divided by bf is width of flange, and check the buckling class. For this we are using table 10, which is available in page 44 of the code. So this you have used in the design of compression members in steel design in your undergraduate BE course. So we have to use the values provided in table 10 of page 44 of the IS 800. So from that you can get the buckling class. There are 4 buckling classes, A, B, C and D. So in which class that member comes, that we can decide. Then after that we have to calculate two ratios. One is KLY by RY, another is KLZ by RZ. Here RY and RZ, they are the actually they are the what is that called Sanders ratio. We are going to take this ratio as Sanders ratio, radius of gyration. So RY and RZ, they are called as radius of gyration about y axis and z axis. KLY is the effective length of the beam column along y direction. KLZ is the effective length of the beam column along the z direction. So these are the Sanders ratio along y and z directions, and obtain the values of FCD from the tables which are given in 42, 43 in the code. So of course we are going to get two values, one along y axis another along z axis. This FCD is nothing but design compressive strength, of course. So compressive strength in bending. So now, after getting these two values, we have to compute two strength values. One is PDY, another is PDZ, which is given by the product of the effective area of the section multiplied by the stress value in both the directions. Of course, here in the case of in this case, effective area can be taken as the gross area. A is equal to AG. In the case of bolted connections, since there will be some holes, you may have to deduct a certain area to get the effective area. Now, once you get these two values, you have to check whether those two values they are greater than or equal to N. So, your compressive strength, bending compressive strength, you are comparing with the axial factored axial load. So, this is another check, which is called as check for member buckling resistance in compression. Now, the third check is check for member buckling resistance in bending. So, this is in compression, next one is bending. So, what we are doing is, we are treating the beam column as a column separately and a beam separately, and we are checking using both the criteria. In both the criteria, if it is okay, then we have to go for the combined criteria. That is what we are doing now. So this here, once this passes this check, the third check we have to do for bending. For that, whatever equation we have used for calculating lateral torsional buckling moment, MCR value in the case of laterally unrestrained beams, which is there in page 54 of the code, same formula we are using for calculating MCR, but one constant we are going to take here. C1 is a constant which depends on the psi value, which I am going to explain when I take up the numerical example in the next class. So this C1 value depends on the psi value. Of course, this is given in page number 129. So, page number 129 of the code book, these C1 values are given. Now, MCR is C1 into root of pi square E Iy. Iy is the moment of inertia of this given section about y axis, which you can get from these field tables. E value for steel you can assume 2 into 10 power 5 Newton per mm square. If it is not given, L square NT. So, that is the effective length of the beam column. G is rigidity modulus. So, which is nothing but some 76.9 to 10 power 3 Newton per mm square. It is not given for steel. IT is the torsion constant, so which is given by sigma BITIQ by 3, which I explained in the earlier lectures videos how to calculate that IT value for I sections. Then IW is the warping constant. So, once again that can be calculated using the formula which is given in page 129 itself, divided by once again effective length square. So, after substituting all these values, you are going to get the value of MCR, which is nothing but the lateral torsional buckling moment in Newton millimeter. So, then we have to calculate one non-dimensional stability ratio lambda LT using this formula root of beta p z fy by MCR. If it is greater than 0.4, then the effect of torsional lateral buckling has to be considered. So, same procedure which we have used in the design or analysis of laterally unrestrained beams, same procedure we are following here. Then we have to calculate some more parameters, phi LT, psi LT, and design bending stress, and then MDZ, that is the design bending strength. So, all these are available in page 54 of the code. So, everything, all the steps, equations are available there. Then we have to check whether the value of MDZ obtained here, it is greater than or equal to MZ, that is the factored bending moment given, which is acting on the beam column. So, this is the third check for buckling resistance in bending. Next, the final check is the combined check. In the case of final check, we have to take both your axial load as well as the bending moment. So, the equations are available in page 71 of the code. It is called as check for overall member buckling resistance for combined bending and axial compression. So, here once again this compression can be in two distinct. One is uniaxial bending, another is biaxial bending. It can be anything. So, here I have given the equation for uniaxial bending. In the case of uniaxial bending, we need to check for only one equation. So P by PdZ plus Kz into Cmz into Mz divided by Mdz, it should be less than or equal to 1. This is for uniaxial bending. For biaxial bending, you have one more equation which is given in page 71. So that also we have to check. So here all these equations are available in page 71. So we have to calculate all these constants Kz and lambda z and FCRZ, of course, we have to its stress value. Then CMZ we have to calculate, which depends on the value of psi z, where psi z is the ratio of the end moments. The higher value is taken in the denominator. Higher value is taken in the denominator, lower value is taken in the numerator. So this psi z value can vary from -1 to +1. So this I have explained in the last class when I explained about the concept of behavior of beam columns. So once you get all these values, so psi z is this value, you will be knowing these two moments. So you have to take the ratio. So once you know that psi z value, get the value of Cmz. So once you get Cmz value, you can substitute here. Mz value is known. Mdz value you have found out that. Kz is obtained from this formula. Here one check is there. This Kz value should be less than or equal to 1 plus 0.8 into P divided by Pdz, where sigma z is once again this value. So where FCRZ is this value. So all these values you can substitute and simplify. Then finally, substituting all the values in this equation 1. In this equation 1, if this sum of these two ratios comes out to be less than or equal to 1, then it is safe. This is in the case of axial load with U, that is one uniaxial bending with one moment predominant. If both the moments are predominant, suppose if My and Mz, in the case of biaxial bending, in the case of space plates, of course, you will come across about both the values of My and Mz. Then you have to use one more equation in addition to this equation, which is given in page 71, and that also has to be checked. So this is about how the section provided for a beam column is adequate or not, checking of that section. So there are 4 important checks we have to make in analysis type of problem in beam columns. In the next thing I am going to explain about the design aspects of beam column. So in the design only one thing is, initially we are going to assume some section based on some criteria. Then that section has been checked for all these 4 once again. All these 4 once again. So only preliminary design we are going to assume some section. Here in analysis is already given the section. So that is the thing. We have to check the adequacy of the section. Whereas in design problem, moments, axial loads, all those will be given. You have to assume a section of your own based on some criteria. Then we have to check whether that section satisfies all these 4 checks. So that is how the design of beam column is done.